So, welcome to this lecture. This is lecture 11. So far we have defined topological spaces and continuous maps between them. Next, we will define continuous maps in terms of limits. We want to define continuity in terms of limits in a metric space. So we will have to define metric spaces and then limits, and then finally give a criterion of when a map is continuous in metric spaces in terms of limits, and that is what is the theme going to be the theme of the next few lectures. So we begin with a discussion on closed subspaces. So we are still not, we haven't reached metric spaces, but we will reach there soon. So definition. So there is a general discussion. The definition of a closed subset is very easy. So let X be a topological space. A subset Z contained in X is said to be closed if the complement X minus Z is an open subset of X. Okay. So recall what we mean by this. So X is a topological space, so it has a topology tau, and Z is said to be closed if when we take the complement that is in tau. So let's make a remark. One easily checks the following properties. Of closed subsets. These follow from the definition of a topology. So the first property is that the empty set phi and the full set X are both closed. The second property is that let Z1 up to ZR be finitely many closed sets then their union Z1 union Z2 union ZR is closed. Okay. And the third property is that let I be a set, and suppose we are given a collection of closed subsets then the intersection of these closed subsets, which is a subset of X, is closed. And all these three properties, all the above properties follow from the analogous properties for open subsets, from the respective properties of open subsets. That's one remark. And the second remark is that suppose we are given a collection of subsets. Suppose we are given a subset S contained in the power set of X, which means we are given a collection of subsets of X which satisfy the above three properties. Right, so S satisfies these properties 1, 2 and 3. Okay, so then let tau be the collection of those u in X such that X minus u is contained in S, belongs to S, sorry. Yeah. So then tau defines a topology on X. So in other words, what this remark tells us is that to define a topology on X, we should either, it's enough to specify the collection of open subsets which should satisfy the three conditions which we saw in the first lecture, either that, or we can specify a collection of subsets which satisfy these three conditions here, and that would specify a topology. Okay, so this remark is left as an exercise. Proof of this remark, prove this. So this is left as an exercise. And another simple statement, which is again left as an exercise, which just follows from the definition. Let X and Y be topological spaces and let F from X to Y be a map of sets. Okay. So then F is continuous if and only if, let's write out the whole thing, if and only if, for every closed subset in Y, Z contained in Y, the subset F inverse Z is, this is a subset of X, is a closed subset. Okay. So the main point behind this exercise is this easy check that F inverse of Y minus Z is equal to X minus F inverse Z. So we have to use this well-known property of the inverse image of a map. So in one of the lectures we saw, after we introduced various ways of specifying topologies, we saw several examples. Yeah? So let's just revisit those examples and see which of those subsets are closed and which are open. Okay? So the first example, or one of the examples we had seen, was the set S1. Right? This is those x comma y in R2 such that x square plus y square is equal to 1. Right? So can we say something about this set? Is this set open or closed? Right. So the answer to this is quite easy. So first we have to make the following observations. So recall that we proved that the set of continuous maps is closed under multiplication and addition. Right? And also that we also proved that the projection maps, the projections from a product are continuous. Right? So therefore this map x comma y maps to x is continuous. Right? So just for fun, let's just make so we have both these maps, x comma y goes to x and x comma y goes to y is continuous. Right? So we can make the graph of this map x comma y goes to y. Right? So let's say this is going to the y-axis. Right. So if we take a small open subset here, right, so the inverse image of that is going to be this strip over here. Right. If this is A and this is B, so then this is going to be 0 comma A and this is going to be 0 comma B. This point here is 0 comma A, this point here is 0 comma B, right? And we have to take this open so the inverse image of this interval is this tube, is this strip, if I may say so, and clearly this is open because given any point over here, we can always find a square like this. Right? This is a picture of the projection onto the y coordinate, and similarly, we can make a picture of the projection onto the x coordinate. So here the inverse image of A comma B will be this open strip So this point is A comma 0, this point here, and this point is B comma 0. Right? And clearly this is also open because given any point here, we can always find a right. So now both these projections are continuous. So therefore x comma y goes to x square is also continuous because this is simply the map. Let me call this map P1 and let me call this map P2. So this is simply the map P1 square, right? So if you want, so x comma y maps to P1 x comma y and the square of this. Yeah. So both these are continuous. Similarly, x comma y goes to y square is continuous and addition is also continuous. So therefore, this implies that. So the results we had proved in the previous class, x comma y square is a continuous map. Right, and now inside R, the subset 1 is a closed subset, right? Because what is the complement of 1? So this is 0 and this is the point 1. So we are just deleting this point. So if I take any x over here, then I can always find a small epsilon such that the epsilon neighborhood around x is going to be contained in R minus. So in other words, for every R minus 1, for every x in R minus 1, we can find epsilon positive such that this epsilon neighborhood around x is contained in R minus 1. Right? Therefore, R minus 1 is open, which implies the subset which contains only 1 is closed. Right? So this in turn implies, so let's call this function, give this function name f. So since f is continuous, this implies that f inverse of a closed subset is closed. So let me just write that. Of a closed subset is closed, which implies that f inverse of this set singleton 1 is closed. Right? But what is f inverse 1? F inverse of this singleton 1 is exactly those x comma y by definition in R2, such that f of x comma y is equal to 1. This is same as saying that x square plus y square is equal to 1. Right? But this is precisely equal to the set S1. So therefore we see that S1 is a closed subset of R2. On the other hand, we could have proved this fact directly from the definitions, because we can look at S1, right, and S1 is this. Yeah. So if we take any point in R2 minus S1, if we could have directly shown, and it's not very hard, that we can find a small ball or a square of radius epsilon which is completely contained inside the complement. So we could have proved that directly as well. Right? Okay. So let's take the second example. Another example which we had seen was the spheres Sn. Right? This is those x0 up to xn in Rn plus 1, such that x0 square plus x1 square plus xn square is equal to 1. Okay, so is Sn open, or can we say okay, let me just phrase it like that. Is Sn open or closed in Rn plus 1, right? And by the same reasoning as above, yeah. So since the function f from Rn plus 1 to R given by f of x0 up to xn is equal to x0 square plus xn square is continuous. Once again, because the projections are continuous, and therefore the squares of each of the projection is continuous, and when we add them, that is continuous. Yeah. So this implies that. So once again, f inverse of this singleton 1 is a closed subset. Sorry. Rn plus 1. So which implies that Sn is a closed subset of Rn plus 1, right? And this is exactly equal to Sn by the same reason as the previous example. Okay. So here are two examples. Another example we had seen was the subset GL and R. Right? This is equal to those A in n cross n matrices, such that determinant of A is not equal to 0. Right. So again, can we say if this is open or closed? So let's look at the determinant map from MNR to R, right? So as an example, let's look at the determinant of a 2 cross 2 matrix. So let's say this is x11, x12, x21, x22, right? So we know that the determinant is x11, x22 minus x21, x12, right? So each of the projections are continuous, so each xij is continuous, and the product of continuous maps is continuous. So this implies that this is continuous. Yeah, and similarly this is continuous. Okay, because the projections are continuous, and this function is the product of two projections, right? So for instance, this first function is x1 maps to x11, x22, right? So this function is continuous. So therefore, so in this case, this is continuous, and in general, we know that, right? Right. So in general, since the determinant is a polynomial in the coefficients of a matrix, right? So this determinant function is actually a polynomial function in the entries here. So therefore, and each coefficient is the projection map, right? And the projection is continuous, therefore polynomials in projections are continuous. So therefore, the determinant map is continuous, right? And now note that GLN is simply the determinant inverse of this subset R minus 0, right? So determinant is continuous, and as R minus 0 is open, right? So this implies GLN is an open subset of MNR. So another example we can take is the set SLNR, right? This is those A in MNR. So is that determinant of A is equal to 1, right? So this is this is closed as SLNR is equal to determinant inverse of 1. Yeah. And yet another example we saw was the set of orthogonal matrices, right? This is those A in MNR such that A transpose A is equal to identity, right? So we claim that this is a closed subset. Right? Yeah, now in each of the above examples showing that these subsets are closed directly could be somewhat complicated, and we see that once we obtain these subsets, once we can realize these subsets as inverse images under continuous maps of certain subsets, so then it becomes a lot more easier. So here also we are going to do the same thing. So first we have to look at this map from MNR to MNR. So let's call this map F. So the map F is A goes to A transpose A. Right. So let's see what this does for a 2 cross 2 matrix. So we have x11, x12, x21, x22. Right. So this is going to map to the transpose of this times the matrix. Right. But this is equal to x11 square, x21, x21 square. This is x11, x12 plus x21, x22. x12 square plus x22 square. Right. So notice that on the right hand side, each entry is a polynomial in the entries of A. Right. And MNR here has the product topology, which is the same as the standard topology. So if we view MNR as Rn square, right. So F is continuous. If and only if each Fij is continuous. Right. So Fij, so in our example, let's say what is F11. So F11 is precisely this coordinate, right? So F11 of this matrix, let's denote this matrix by X for simplicity of notation. Right. Similarly, F12 of X is equal to this coordinate, that's X11, X12 plus X21, X22. Right. And similarly, we have F21 of X. This is X12, X11 plus X22, X21, and finally we have F22X. Right. So all these, each of the coordinate functions, coordinates is a polynomial in the entries of X. In other words, each of these coordinate functions, we can write it as a polynomial obtained using the projection maps. Each of the projections is continuous, and since we take product and add, etc., that's also going to be continuous. So therefore, each of these coordinate functions is a continuous function, which implies that the F is a continuous function, right? Because so we can view F as a map from MNR to MNR. Well, standard topology or the product topology, it doesn't matter, because as we saw, the product topology on Rm is same as the standard topology on Rm, right? So therefore, so this shows that F is continuous. Right. And now, so note that. So this is for the 2 cross 2 example. Yeah. So in the n cross n situation, or let me not write this. So you can write down explicit coordinates for general n, right? So what are Fij for general n in terms of Xij? So this is an easy exercise. So you can just write this down. Yeah. In any case, this shows that F is continuous in general. Yeah. So f is from MNR to MNR and it is continuous. So clearly this ONR is equal to f inverse of the identity matrix, right? So MNR contains the identity matrix, yeah, and therefore to show that ONR is closed in MNR, it suffices to show that this singleton identity in MNR is a closed subset. Right? But this is a very general result, so we will write this as a lemma. Right? So let A1 up to AM in Rm be an element. Right? So let's denote this by A. Right? So then Rm minus this point A is a closed subset. Okay, so proof. This is left as an exercise. So we will end here.